Hello YouTube, and welcome to a teardown of a failed DJI Inspire 1 battery. There's a couple things to know out of the gate. Lithium-ion batteries are not a safe thing to take apart as a general rule unless you know what you're doing. I have a couple of things in place on the side here. We have a metal tray and a large bucket of salt. If it were to attempt to immolate my desk, we can then bury it in the salt, which should, in theory, put out the flames. So, without further ado, it looks as if this battery is held together with clips. It may or may not have adhesive or glue as well. So, if we gently work at this edge here. Okay, so it has more clips on the side. I'm going to grab a couple of shims to try and shim the sides out. That should give us a release on the clips. Yes, there are indeed clips here on the side that we'll have to shim open. Hopefully we can get this open without having to use unreasonable force. Almost need 3 hands. There's one for the clips. Same process for the next one. If you're curious, these are just thickness checking, spark gap checks, spark gap gauges. There we go, there's 2. I do not want you attempting to service this battery on your own, for sure. Try and not break it in the process, even though it is most likely already junk. Alright, there is shim 3. One more to go. And we should be able to get the side open. Alright. These 4 shims in place. These clips should not hamper us as much trying to get this open. Here's one side. Aha! There we go. Slide these out of the way. Okay. So, gently lift this up. We can see that we've got positive terminal, negative terminal, and what appears to be balanced leads for the battery pack. We'll gently unplug that. And we'll take these screws out to grease the board. This little battery has a lot going on. It is not just a simple charge controller. It has an awful lot of brains. The DJI likes to put firmware in everything, and even the batteries have firmware that has to be updated. So this thing's kind of a nightmare to work on for a hobbyist user. One more screw. And we're loose. So a little bit of clear plastic, sort of kind of fiber optics here for the LED array that gives battery status. And you can see these little tiny surface mount LEDs. These little white squares here, 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 and here. Gonna unclip this charge balance lead gently. So it appears that not only does it have a charge balance lead, but it also has a relatively intelligent communication back to the drone itself based on this dual pin feedback mechanism, as well as the main power connector. This battery, you can feel, has a problem because it's puffy. Also, I do not know if it is full, mostly full, so I'm going to be very, very careful with this battery. Those are very robust electrical connections, a lot of current on these drones as they fly. And not shred all of this insulation paper. Not that we'll probably be putting it back, but you can see all of these tracks have been heavily reinforced with solder for increased current carrying capabilities. I am going to pause the video here for just a moment and go get a multimeter, and we can take some measurements off the battery. Alright, so I went and grabbed the Fluke multimeter, good old trusty Model 179 Fluke. It is a auto ranging multimeter, so all we're gonna have to do is turn it to volts DC. And let's see what we've got here. This pack is showing basically 0 volts, so it is most likely completely dead. Yeah, so we've got negative 0.698 volts on what should be roughly a 22 volt pack. So it is most definitely failed in the battery. So at that rate, I am not nearly as concerned with breaking it or it lighting on fire on my desk. So let's turn the soldering iron on here. Get this apart a little further. If you guys don't have one of these and you've got a soldering iron, these are the best things since sliced bread. These are much better than wet sponges. Waiting for the iron to come up to temperature here. It'll be about 650 degrees Fahrenheit. And let's see if we can get enough heat on this. Get it to let go. We may need to use a little bit of extra solder to get the temperature to flow. A lot of times they use a lead-free solder in modern manufacturing, and the truth is lead-free solder is just awful. A little better for the environment, way worse for people to work with. slightly lower temperature. There is a lot of mass here, so it is not quick to warm up. Relatively high temperature solder. I'm going to bring the temperature of the iron up a little bit here. Usually work on stuff that's slightly more delicate than this. That's why I've got the fine tip on here. Come on, melt you. There's a lot of mass there. I may not have enough iron here on the desk to be able to get this apart. There we go. Cool. It doesn't look... Nope, it did not pull the track off the board. We're good there. But that is a very, very large connection. These two extra wires here look like they are probably for a temperature sensor for battery overheat. We're going to try and get this other end here off using a very similar process. Pull a little bit of solder to get a better connection and just let it heat and come apart. Soaking up a lot of heat here. Even the wire up near the top is starting to get pretty warm. And there we go. So, looks like next thing we need to do is get this little red jumper out of the way. And like I said here again, normally I would be a little more concerned with shorting the battery, but as we've already established, it is dead. So, let's see what we can do. This lead-free solder is just terrible. Makes conducting any heat at all very difficult. It's got a much higher melting point and also tends to oxidize and prevent good contact with the iron. Gently try and remove this. There we go. You want to try and keep as much heat out of the electronics and out of the battery as possible. Electronics don't like heat in general. Some of this stuff is a lot more robust than you think it is. You hear numbers thrown around like 80 degrees Celsius for processors and things like that. That's more of an operating threshold than true max before damage. Some things are relatively sensitive, some transistors and things like that, but a lot of this stuff is a little more robust than you'd expect. There we go. I am going to see here. I don't know if I can get these two little leads with what I think is this thermistor, and they are mounted on the bottom of the board under a celastic material. So this is to prevent or help prevent vibration from breaking those little leads loose. I'm going to see if we can finesse this battery out of the case at this point. It may or may not come loose due to it being swollen inside the case. You can see the case is actually puffed out here on the sides. It also may have some glue or tape. Oh, it looks like the whole case splits. That's handy. Let's use that to our advantage. Come out. Yeah. So it feels like there's some glue clips in here at the bottom. There we go. Yeah, indeed there was some double-sided tape holding this battery in. Not a bad thing, just one of the things to know if you're going to take one apart. Alright. That is indeed a little thermocouple to monitor battery temperature. And it's just glued in. There's no good way to get that apart without breaking it. Oop. I don't know if that broke the thermocouple or not, but that is definitely a temperature sensor. So, right here, warning, they do not want you to open this. They say no user serviceable parts inside, and that most likely is the case in this battery's case. This is 6 cells, 6 lithium-ion cells, and they are stacked. These are aluminum. May or may not be for heat dissipation. Gotta be careful with these, especially when they're alive and good. These soft side cells are relatively fragile, but you can see right here. See how these puffed up? These are definitely bad cells. This is an interesting design. You can see that they are ganged up. Appears to be 2 banks. 4.2 volts peak lithium-ion cells. They are 8.3 watt hours at 3.7 volts nominal each cell. And then there is 6 on this side and 6 on this side, so 12 total cells. Most likely they are all junk due to the voltage they've been sitting at. It looks as if looks like they are using these two are in parallel. It looks like, yeah, so it looks like they're using a combination of parallel and series cells to get more current at the 22.2 volts. Do a little bit of quick math here. Yeah, so they are definitely doing a series parallel combo. So it looks like they're pairing 2 of these flat pack cells together. So you effectively have 3 larger batteries on this side and 3 larger batteries on this side at 3.7 volts each, giving you 22.2 volts total for 6 battery banks. it is unlikely I will be able to get these apart. They are a relatively interesting layout. Yeah, they're all stuck together with foam tape. I'd like to get them apart and see if any of these cells are any good, because some of them look like they might be okay. So these ones are puffed. These ones here, this set is puffed, but this set is flat, and that's at least a decent sign they might be okay. Let's see if we can get any of these to release. I have a feeling I would need a much larger soldering iron to do this effectively. Get enough heat on it. But we'll try. You can see just how slow this flows out temperature-wise. This iron's just not quite big enough to do this job. You gotta be careful and feeling for heat transferring into the cells. They're not real happy when they get hot. No, I don't think this iron's gonna pull that much heat out. Alright, let's do this slightly differently. Let's see if we can... Tell you what, let's check some voltages at different points in the cells here. 0.7, pretty low. What I'm doing is I'm checking the individual parallel banks. Yeah, so it looks like that 0.6 volts we were seeing across the entire pack was all being provided by this one parallel bank here, because if you measure it separately, it is at 0.704 volts. So if you measure across the entire pack, you get 0.708. Only 0.004 volts is being added by all of these other banks. So this battery is completely toast. Question is, and I don't have a good way to check and see, is what caused this battery to fail? Is it bad battery? Could it be a bad charge controller in here? This battery only has a few cycles on it, so makes one question if this was a defective part to begin with and either overcharged or let the cells sink to less than storage voltage and sit empty. Lithium-ion batteries, they don't like to sit full and they don't like to sit empty. If you're going to store them for any length of time, I would highly recommend storing them around 3.5 to 3.7 volts DC per cell. That's about 50 to 70% charge. They're much happier to stay at that voltage long term. It's a neat battery, not very serviceable, and unfortunately we don't see anything that looks to be a direct cause of failure. I don't see any burn marks or scorching on the board. It appears that the cells just have failed and either not recharged or drained. Things that could have happened is if this board was draining power slowly, if it had some sort of amperic draw just in storage, it could pull the battery down, and they don't have to sit very long at all at below 3 volts before you get permanent damage. So it's a pretty neat battery, neat technology. DJI did a good job packing a lot of power in a very small form factor. Definitely not user serviceable. Wouldn't exactly recommend anybody else tear these down. If you do, please be careful. I think that's it. So Hope you all have a great day, and thanks for watching.